Unleashing the power of the sun in a perfectly safe and controlled manner and harvesting it is an old dream of mankind. Welcome to this short video presentation, which shall give a brief overview of what can be achieved by using software developed by the Saxonian Institute of Surface Mechanics, SIO. In this example, a multiple impact scenario hitting a chamber wall of an atomic fusion device is simulated. We will see that certain impact compositions can damage the sample even if the single contacts alone are not critical at all. An optimization with an added protective layer will be simulated, and finally a second optimization is done with the help of tailored intrinsic stresses in the surface. The subsequent optimization of these stresses is performed by the IStress module developed by SIO. The software applied here works completely scale invariant, and we point out explicitly that the chosen example of particles hitting a fusion device is just one possible application. To simulate the behavior inside a fusion chamber, a distribution of 6 impacts containing 3 different impact particle sizes, energies, hardness, and effective elasticity is evaluated. The impacts partially overlap in contact, time, and space. The stress field calculation with the software Fimldoctor on the right-hand side show that a small impact could create a zone of plastic flow, here marked as blackened areas, within the substrate, and this way harms the integrity of the system. Thus, a protection of the substrate is of need to prevent such damage. Here we see that a medium-sized impact is relatively uncritical for the substrate, so that it doesn't necessarily need to be protected. And a big impact, finally, in our case is completely uncritical for the substrate, so no protection of the substrate is needed. In reality, however, not only one impact hits our material. It is always a combination of different impact types with different counterpart sizes and energies. This can lead to overcritical situations even in those cases where the simple impact would have no effect. So, a protection of the substrate is also needed against such worst-case multi-impact scenarios. The first idea here is we add a protective layer on top of the substrate. In this video sequence here, multiple impacts hitting the unprotected surface of a fusion chamber wall is demonstrated. We see that the different counterpart sizes which hit the wall surface with different energies. With the help of the software Fimldoctor, we now produce a 3D animation which shall visualize the impingement. The impact counterparts hit the wall's pure substrate from above, and we see that the critical regions lie under the substrate surface and are shown as red areas. The black fields are special colorings in order to visualize the critical areas. Here, plastic flow will occur, and thus the material will be damaged permanently. On this basis, we can now try to protect the substrate by coating it with an additional layer. Again, the software Fimldoctor helps us with the calculation and prediction. Now we see that a small impact creates a small plastic zone within the protective layer, but no plastic zone in the substrate anymore. So the substrate is protected. More complex coating material and structural optimization might help to even further improve this very simple first-level protection. A single medium-sized impact does neither create a plastic zone in the protective layer nor in the substrate. Thus, the layer is protected. And finally, as expected, a single big impact does not create a plastic zone in the protective layer nor in the substrate. So the fusion wall substrate would be protected as well. We saw that for the single impacts, the layer indeed protects the substrate. But a distribution of a few impact counterparts within a bad case multiple impact ensemble still led to plastic flow within the layer and the substrate. The following videos show the stress distribution over time for a sequence of 6 impacts with 2 impacts of each size. The green areas are absolutely uncritical for the layer or substrate, whereas orange and red get more dangerous for either the layer or the substrate. Then we repeat this calculation, and to point out the most critical regions, all dangerous areas are now colored in black. So the black spots here indicate dangerous zones of plastic flow where the material will be damaged permanently. The SIO software Uncertainty Budget Calculator now evaluates the uncertainties of the process by taking into account the unknowns, or not accurately known, parameters and the ranges of variation. The animations show the stress distribution over a time for a sequence of 6 impacts with 2 impact situations of each size. In the middle frame you see the standard, normal or average case. In the upper left corner, however, we see the results from the software's calculations taking all uncertainties of a possible worst-case scenario. And the last video frame shows the calculated best contact cases. Green and orange are uncritical, but the dark red zones are dangerous for the substrate layer combination. Here the same calculations are repeated, and this time all dangerous areas blackened again. They indicate plastic flow or otherwise permanently damaged material. We see that even assuming the best case for all uncertainties and variations, the material is still damaged. We have seen that a protective layer helps a lot, but it can still happen that some impact combinations damage the sample. So we need another optimization step. A few options are thinkable here. We could change the layer properties like Young's modulus, thickness or yield strength for the example. We could add a second layer or even more interlayers. But we could also change the intrinsic stresses of substrate and protective layer during the deposition process. The software IStress optimization creates a profile of intrinsic stresses which helps to create the application performance of our sample. With the help of this easy-to-use model, you can simulate desired intrinsic stresses within the substrate and/or the layer, or even in a multi-layer stack, and find out which might come in handy for our special application. This animation again shows multiple impact situations on our fusion chamber wall, this time with incorporated optimized residual stresses. We can see that there are no longer areas of plastic flow, neither within the layer nor within the substrate. Here now we use again our uncertainty budget calculator and show 3 animations of different contact situations in an overview. In the middle frame, the standard or average case. In the upper left corner, the results from the software's calculations taking all uncertainties of a possible worst-case scenario. And in the last video frame, the calculated best contact cases. Green and orange are uncritical. The dangerous red zones are only to be found in a really worst-case scenario where all uncertainties are not in our favor. Here comes again the same calculation, this time once more the remaining critical areas visualized in black for highlighting and a better understanding. To conclude, in the example of multiple impacts hitting a fusion chamber wall, calculations with the software Fimldoctor revealed that especially speedy small-sized impact counterparts might be dangerous for the unprotected substrate of the chamber wall. 3D animations showed that an additional layer put on top of this vulnerable substrate can significantly improve the situation, but cannot prevent plastic flow and thus permanent damage completely. In a further optimization step, the software module IStress helped to simulate a variation of the intrinsic stresses of the substrate and layer which could be practically done during the coating deposition process, perhaps via proper bias adjustment. Thus, the software IStress optimization creates a profile of intrinsic stresses which helps to increase the application performance of the sample. In result, the incorporated optimized residual stresses help to prevent areas of plastic flow within the layer and within the substrate. Finally, the SIO software Uncertainty Budget Calculator evaluated the uncertainties of the process by taking into account the unknown parameters and the ranges of variation. Animations visualized that by using intrinsic stresses in a one-layer substrate combination would indeed protect the fusion chamber wall against investigated impact counterparts very well, but still, worst-case assumptions could harm the system. Again, we point out here that the used software works scale invariant and could be used in many different but similarly demanding applications. We thank you very much for your attention. If you have any questions or remarks, please feel free to contact us under the email address below.